Hello, ladies and gentlemen. Welcome to the second day of the 2021 National Virtual Work Zone Management Conference. We're very excited to have you here today. We have a wonderful set of presenters giving all kinds of fantastic information. But before we begin, I'd like to kick it off by welcoming ARPA's Robinson Vasquez up to the stage. Robinson's going to tell us about an upcoming training program that looks pretty exciting. So go ahead, Robinson.
Thank you, Matt, and happy St. Patrick's Day for everybody. I have a gift for you. If Matt, can you help me to share my presentation? We are promoting, or we have a trenching and excavation safety training free from everybody. So I am going to share the information. It's going to be provided on Thursday from 8 a.m. to noon. It's a very, very comprehensive training about excavation and safety training, and we are going to be provided via Zoom. Similar to this training, we are also providing several other courses related with roadway construction safety. Let's say run over sandbag covers, silica protection, safe backing and spotting, fall protection. We do the OSHA 10, OSHA 30, the ARBA 14, which is especially for leaders in roadway construction. It's more than the ARBA. It's a sort of a middle point between the OSHA 10 and the OSHA 30, especially focused on roadway construction safety. So everything that we have, we are now providing virtual training, and also in the future, we are going to provide it also face-to-face training after this sanitary emergency we are suffering now is over. So just, I'm going to send this information in the chat box, the link to register for this class on Thursday, from 8 to noon.
Yep, I just pasted them in there for you, Robinson. So you're set. Take a look in the chat box, everyone, in general chat. You'll see the Zoom request and a little more detail and a link.
Excellent. Thank you so much, Matt.
All right, thank you, Robinson. So you can go ahead and turn your camera and mic off. And I'd like to welcome up to the stage Mr. Brad Sant, who will be providing us with his moderating skills for the next session. So Brad, come on up.
Thank you, Matt, and I'm glad to welcome you here again on this St. Patrick's Day for day 2 of our conference. Our next session is a really exciting one. We have a number of people who are going to be talking about what's going on at the Turner Fairbanks Highway Research Center and a lot of the great research that's going on related to work zone safety. So first up, we have Tony English with NARA Consulting, and Tony has over 20 years experience in IT and ITS. He currently leads the engineering efforts with the Wyoming DOT Connected Vehicles pilot and leads system engineering architecture for CDOT CV projects. He has worked on projects with the U.S. Department of Transportation to dynamically map work zones using the RSM and the WZDX 3.0 messages. His backgrounds includes mechanical engineering and robotics. So let us begin welcoming Tony English.
Thank you. So the work zone project that we finished up this past December, it really focuses on the ability to map work zones, edit work zones, produce the RSM message, the WZDX message, and manage the life cycle of these messages with a cloud component and a PC or cell phone component. But why should we really care about this? What's our real focus on these applications and this data set? We're really looking at ways to improve the safety of the work zones, increase the knowledge about the location, the lanes, the information within the work zone, and allow for easier, more efficient ways of navigating through the work zones safely. Next slide, please. So how does the tool work? It starts out with a IOO user putting in information about the work zone. They're going to put in a lot of data about the beginning points, end points, speeds through the work zone, lanes that are available, that sort of thing into a website. That's going to build out a configuration file that you see in the upper left of the screen there. Once that configuration file is built, then the persona changes to a construction manager who's going to actually drive the work zone. They're going to do it either with an Android cell phone or with a Windows PC, tablet, or laptop. That's going to gather some breadcrumb information as well as some metadata about the lanes, where the workers are, information that's going to be fused together with that configuration file. Then in the upper right, you see the improved work zone description, and that's going to include the mapping information with the configuration data. That data gets verified, it gets edited, and then finally published out to third-party applications. Next slide, please. So how does this work? We've got some back office tools in the TMC or at the IOO. That's going to be the work zone configurator, the generator for the WZDX, the RSM messages, different ways to visualize both the WZDX 3.0 message is what we're currently working on, as well as the RSM message, so that 2945/4 message that's in final ballot now. It's not quite out yet, but should be soon. And then publish both those messages, the GeoJSON message for the WZDX, and then the OOPR, as well as the XML message for the RSM, to different types of third parties. Then there's the field gathering data. With that, it's the ability to gather those breadcrumbs and then associate the metadata with those breadcrumbs. Tie those two pieces together to build out an accurate representation. Next slide, please. So how does a little bit more detail about how this all fits together? How do we tie these things into the information that we're providing? So we've got that IOO user in the upper left, building through that configuration creator, saving that data to that Azure cloud storage in the center right, and making that data available to the construction manager at the bottom of the screen there. That's going to go out and grab the vehicle path data, build out a CSV with the breadcrumbs, store that back up into the Azure cloud storage. There's some functions that get run on the aggregation of both the configuration file as well as those breadcrumbs, and that's going to generate the RSM message. And then we've also got a translator that's going to build out the WZDX message. Those will be saved into the cloud storage, and then it's available back in the TMC website for the IOO user to go through that visualization, the editing, so if workers move or lanes move, the verification, and then finally the publishing. Once it's published, those messages are available to third-party groups, so you can do center-to-center type communications with the WZDX messages. CDA for automated vehicles, that's going to be more of the RSM type message, the super compressed message. And then we've got an easy way for third parties to integrate with this with the SDX API, and that's integrated in for a nationwide availability for pushing out the WZDX information. Next slide, please. So this is a little bit of eye candy. No real intention for you to be able to see exactly what's on each of these screens, but let me give you a quick overview. This is the 6 tabs of the website that the IOO uses to build out the configuration information that we've talked about for the work zone. In the upper left, there's some naming stuff there, some road names. What are we going to call this work zone? In the top center, it's got the lanes, the speeds, the lane widths, padding, different types of construction codes for the work zone, when the work zone's active, days of the week, and between different days of the month. In the upper right, there's the beginning endpoints. You can do a search there with the Google Map API to quickly find where you want to place those anywhere in the nation. In the lower left, it's adding a lot of data about the WZDX message. So it's got a lot of good information in there. So you can lay out specific information about what kind of construction is being done and where it's being done. In the center, bottom center, there's restrictions. So if you have a lane that's got a truck restriction or width restriction or something like that, you can add that data in, and that also adds a little bit more color to the WZDX message. In the bottom right, you can set up your LRS type. So how are you gathering this data? Is it survey? Is it GPS? That kind of thing. So you have really quite a rich data set. Then you go out into the field. The pictures that we've got here are from the Android application. The Android application can either use its internal GPS, which is fairly low resolution. We've tried a bunch of different modern Android phones, but without the antenna on the roof, it's light resolution and accuracy there. I'll go into a little bit more detail on that. But if you have a decent U-Blocks that you plug into your Android phone through the USB connection, it'll auto-detect that and leverage that. You can go from a 1 hertz to a 10 hertz data collection and much more accurate HDOP values so that you get down to that lane level resolution of your breadcrumbs. So it automatically detects that sort of thing. It'll automatically start and stop when you enter and leave the work zone. Once you finish it, it'll auto plot the work zone and put that on a map, and then it'll allow you to upload that work zone. This solution allows you to work out in the field where you do have internet so that you could download these config files, or you can pre-download all of the work zones that you're going to go map at the beginning of the day, and then you can upload them whenever you get back into internet range. So you can either automatically upload that at the end of the run if you happen to be in LTE range, but if not, you can upload it later. Next slide, please. Not seeing the next slide. There we go, perfect. So this is a quick overview of the internal GPS versus the external one in a cell phone. So you'll see like the 5 meter accuracy and the 1 hertz resolution with the internal GPS versus the 10 hertz and 1 meter approximately lane level accuracy. Next slide, please. So once you're back into the cloud environment, you can edit the work zone. If people call in over the radio and say the workers have moved or the lane closure or the lane opening has moved, you can adjust those within the work zone. We're using the MUTCD lane tapers, and those are just automatically generated at the beginning and end when you have those lane closures. When you only have 1 hertz data, it just generates the WZDX message, so that's more longitudinal. When you have the 10 hertz, the more accurate GPS, then it does the longitudinal and the lateral, so it'll plot out every lane using the RSM message. So once those are edited, you can publish those out and make those available to the third parties. Next slide, please. So all of this is available to publish, download. It's enabled on our website. You can generate this, mess around with it. It doesn't require any credentials at this point. It's strictly a proof of concept. Down the road, we'll probably look at doing implementations with it that'll have a little bit more scalability and that sort of thing. Next slide, please. This is the final slide, and future enhancements. So some of the things that I think would be convenient to do is to add in to the Android app something that you could bring in a vehicle with you. So if you were a driver, so add in a new persona, and it would just give you an alert if you're going over the speed limit into a work zone. It would give you kind of a beep, beep, beep type thing. It could notify the users of alternative ways to get around work zones. Speed limits, lane closures, that type of thing. we could also extend that application so that the workers could be in a worker mode, very low battery drain type mode, where it would occasionally, maybe once every 5 minutes, upload the worker location and then update those based on where the workers are located. Could be integrated in with icons. I think that would be really convenient so that you get those updates for the work zone data. Handle more complex work zones, varying number of lanes, detour routes, things like that we don't do currently. At the moment, we are doing some integration with the Karma Cloud and the automated driving systems, so that's getting pushed out. We've got some links in there of some videos of it running, the GitHub site and the website where this is all posted on. That concludes my presentation. Thank you for your time.
Well, thank you very much, Tony. Very interesting information that you're putting together, and I hope we'll see more details on that as it gets fully developed. Next up, we have Jayshree Iyengar with Leidos. And Jayshree is the principal investigator for the OSS4 ITS project and is responsible for coordinating and developing the project requirements and the architecture for the OSS4 ITS application suite. We'll learn more about what that is. Jayshree is also the Scrum Manager for the V2X Hub project and provides project management support for the team. So welcome to the stage, Jayshree.
Can you hear me?
Yes, we can. You're set.
Hi, Brad. Are you able to hear me? Okay. All right. Hi, everyone.
Loud and clear. Thanks.
Okay. All right. Sounds good. Hi, everyone. My name is Jayshree Iyengar. So I'm going to give you an overview of the OSS4 ITS project. We're going to look at the 4 projects under the OSS4 ITS umbrella. We're going to discuss some benefits of OSS4 ITS, and I'm going to provide you the available resources and provide you the links. Next slide, please. So open source for ITS or OSS4 ITS is an ecosystem that promotes deployment of interoperable ITS systems. It's a suite of open source applications that represent different areas of ITS infrastructure. The software suite will provide IOOs, software companies, and device manufacturers a clear picture of the available open source software tools for both technical and business needs. OSS4 ITS project will ensure that all the application architectures and backlogs are communicated and coordinated among the teams for a full complement of the collaborative tools that we are developing. Next slide, please. Okay, so the 4 projects under OSS4 ITS, they include Vehicle to Everything Hub or V2X Hub, ODE or Operational Data Environment, Secure Data Commons or SDC, and Karma. All of these 4 projects within OSS4 ITS ecosystem have been working collaboratively to develop a unified software suite to reduce redundancies in architecture and reduce overlaps and gaps and promote the reuse of code. We started working on projects independently, but over time, we've been doing more and more collaborative and coordinated efforts among the projects. Next slide, please. Okay, so the first project under this is V2X Hub. It's a multimodal open source software that acts as a message translator and enables network communication between infrastructure, vehicles, and personal devices. It's an interface system that supports collection, integration, and dissemination of data among different infrastructure and vehicles for a variety of applications. And it's usually deployed at signalized intersections. It has a built-in message translation, and it uses a plugin architecture, which enables it to reduce the amount of back-end work needed to integrate, for jurisdictions to support connected vehicles deployments. Its goal is to improve safety by adding connected vehicle technology deployments. It promotes interoperability between different actors in the connected vehicle ecosystem. Again, it's multimodal by enabling the communications between vehicles, infrastructure, and the road users. It's integrating the existing systems that are in place, like the traffic management systems and connected vehicles using networked and wireless communications. And I was mentioning that it has plugin architecture, which each of those plugins are software components. They provide a specific or a particular function. We have preemption plugin, we have map and spat plugins. There's a curve speed warning plugin. There's a BSM logger plugin. There's multiple plugins used within V2X Hub. The core software provides the framework for message exchange between radios, and it also allows for conversion of the messages between different protocols like SAE and NTC IP for data exchange between signal controllers and vehicles. It also provides message encoding and decoding for the protocols required by the SAE standards. Next slide, please. Oh, okay, you're already there at the next slide. Sorry, yeah, that's good, thank you. ODE, or Operational Data Exchange, is a real-time data acquisition and distribution system. It functions as a middleware by brokering, processing, routing data from various data sources, including connected vehicles, field devices, and TMC applications. So ODE can accept data from connected vehicle applications and broadcast them to field devices through RSUs and situation data warehouse, which in turn will transmit the data to Sirius XM satellites for delivery to connected vehicles in the field. ODE also provides the capability to sanitize the data, like scrubbing any PII info from the data, so that the data can be used for further operational and research needs. The data users include transportation software applications, research data exchanges, US DOT situation data warehouse. So ODE is basically a cloud-based version of V2X Hub that facilitates the communications between various traffic management systems and vehicles, where the field V2X Hub implementation is required. Next slide, please. Thank you. SDC, or Secure Data Commons, it provides a cloud platform for data providers to contribute data, define rules to access the data, and allows collaboration between data analysts. Data analysts can request access from the data providers for big data sets in part, which is the geofence data, or in full. And the data can be analyzed in the cloud with many pre-installed analytical tools provided on cloud-based Linux or Windows workstations. And the derived data can be exported with permission from the data provider. There's 3 different ways of data transfer updates provided. Real-time data transfer, which is the streaming data, batch data, which can be daily or weekly, and ad hoc, which is occasional data. And SDC offers an authorized and controlled access to individual data sets, as well as the metadata associated with those data sets. Next slide, please. Karma is an ecosystem, which is a network of open source software applications that all work together to accomplish the overall Karma project goal of using CDA to improve transportation mobility, efficiency, and safety. Karma's vision is to provide open source software and enable a plug and play devices. It's technology agnostic. It encourages industry collaboration. So Karma is a multimodal effort between FHWA, FMCSA, ITS-JPO, MARAD, and WOLPI. Next slide, please. So Karma's product suite contains multiple tools. And also, I wanted to also mention one of the things is we've divided, we're actually aligning the Karma program into 3 different tracks, which is basically traffic, reliability, and freight. The traffic track is going to explore the applications or use cases related to recurring traffic congestion, on freeways and arterials. Reliability is going to explore applications and use cases related to non-recurring congestion, for say for work zones, inclement weather, and such use cases. Freight will be, doing the CDA applications for commercial motor vehicle operations and port management applications, as well as traffic platooning applications. Karma product suite contains many different applications. They're all open source applications. Karma platform is the downloadable platform which can be downloaded to the vehicles. It's built on top of Robot Operating System, or ROS. It utilizes open source software that enables CDA features to allow ADS systems to interact and cooperate with each other and infrastructure, through different communications. Karma Streets is an edge computing application for use cases such as sharing perception data, from the edge devices deployed in the infrastructure like LiDARs and cameras with the vehicles, and also infrastructure assist applications like curve speed warning and corridor management. Karma Messenger is an application that enables communications between manual vehicles and CDA vehicles in use cases such as flyby inspection for vehicles for freight applications, or broadcasting in-field geofences for work zone and incident management use cases. Karma Cloud is a cloud-based open source software that enables communications between cloud services, vehicles, and infrastructure and road users. Karma Analytics supports analysis and management of the cooperative automated vehicles data that we collect and the traditional transportation data. Thank you. And the next slide, please. Some of the benefits of OSS for ITS. One of the main benefits is to ensure that there's collaboration between the 4 projects, SDC, ODE, Karma, and V2X Hub, to develop a unified software suite and provide a single point of entry to ask questions and get technical assistance. Deployers can accelerate their programs by utilizing and reusing and augmenting the OSS for ITS tools. And we're actually identifying overlapping software to reduce any redundancies between architecture and documentation, and encouraging reuse of code. And one of the key deliverables that we have for this project this year is coming up in July. We're going to be demonstrating a combined software suite, all of these applications together for a reference implementation demo, which will basically integrate V2X Hub with the WZDC tool that Tony just mentioned prior to my presentation. We're going to integrate with the tool to collect the data, to upload and download WZDX and RSM messages. So we can do that one of 2 ways. We'll either poll, we're going to do, as V2X Hub will poll the WZDC tool for the list of RSM files that have, their new RSM files or any updated RSM files from WZDC and publish them to RSU, which will broadcast them through the OBUs to the Karma connected vehicles, so the users are informed of the work zones that are coming up. And the other way is the WZDC tool will push the new RSM messages to Karma Cloud. And then Karma Cloud will actually process those RSM messages, convert them into a TCM messages, and push it to V2X Hub through the existing solution. So that way the users will be informed of the work zones coming up. Next slide, please. So these are all the available resources. So if you go to ITS Professional Capacity Building Program page, that lists a bunch of resources that are available. CAV Support Services will provide IOOs, equipment manufacturers, and device vendors technical assistance. There's also equipment loan programs where users can become familiar with the types of equipments that are used in CV deployment, like RSUs, OBUs, packet sniffers, SPAT and map message test devices. There's also a toolkit called Cave in the Box, which will provide hands-on learning experience for users. There's also help desk support. There is, OSS for ITS resources where you can find, you can find the links to all the projects that we're working on, the conference pages. You can get through there. And also there's ITS standards. There's links to the standards. There's training provided and access to data and code, because all the source is open source software. So this is all available for public and private use, and also for academia. There's also technical reports and primers available from US DOT CV pilots. Next slide, please. Are you able to hear me?
Yes, we are. We can hear you just fine.
Okay, sorry, I got locked out.
Okay.
Okay, sorry about that. Okay, so if you go to OSS for ITS conference homepage, that's a great point to get started with. You can get access to all the documentation. There's architecture. We have the roadmap provided. There's all kinds of metrics collected. You can find, different kinds of information for all the different projects that are that we're working on together. It's a collaborative platform, so we're all working together with that. You can also reach us on the OSS for ITS email address that's provided there. As I mentioned earlier, CAV Support Services email, that's a great point to, to reach out. I've also provided the WZDX support email to reach out for any questions and information. And next slide, please. I just wanted to mention that Deb Curtis is our GTM, so her information is provided over there if you want to reach out to her directly. And that concludes my presentation. Thank you very much.
Thank you so much, Jayashree, for your presentation. We really appreciate that. What we're going to do, I noticed a couple of questions right now in the Q&A session. So folks, if you have questions, don't put it in the general chat. Go to the far right and put it in the Q&A. I see a question from Michael and from Paul here. We're going to take and put those, let the panel address those questions at the end. So if you might just modify your questions, if you have them directed to a specific panelist, so we know who to direct those to, because those have come up at different times, and I'm not quite sure who you were questioning. So we'll take those questions at the end for the panel. All right, so to stay on track, next up, we have Jay Parika with Camp LLC. And Jay began his career with the automotive industry as a research engineer at GM in 1985. At General Motors, Jay was involved with various projects in wireless communications, including the development of mobile ad hoc networks for intravehicular and vehicle to infrastructure V2I communications for safety, mobility, and ADAS applications. Since 2014, Jay is involved at CAMP as the principal investigator of the V2I consortium responsible for development of wireless communication-based safety and mobility applications under a cooperative agreement between CAMP and the Federal Highway Administration. Mr. Parika holds a BS and EE degrees in MS and a Master's of Science in Computer Science. So welcome, Jay, to the stage.
Can you hear me now? Thank you, Brad.
Yes, sir. You're there.
Okay, thanks. Thank you so much for the opportunity. I think this is probably the second slide. So can you go one up? So just for this is an acknowledgement and disclaimer, like Brad just mentioned. CAMP project that I've been involved with is the cooperative agreement between Federal Highway, and the information that I'm presenting here is of the project and the camps and not necessarily of the Federal Highway. Next, please. So why do we need infrastructure map for CV applications? Almost all connected vehicle applications that communicate with the infrastructure requires the map information. The reason being, vehicle needs to know where it is and what is coming up ahead to know whether it's entering into a work zone, a curvature, a signalized intersection, low bridge, whatever that might be. But in all these cases, a map is essential element. And one can look at a map in a, as defined here, in three different areas or three different categories. A low fidelity map, such as low fidelity map, just provides you a region, and region tells you that within this region or going northbound on a specific direction, the certain the freeways or the roads are closed due to certain conditions. That gives you enough information to the traveler that something is closed, but not enough to tell the drivers or even the automated vehicle to know which lane it is and where it is and so forth. So when you go to from a region which comprising of a large area to a specific area on a road directions and how long it is, such as medium fidelity, that gives you limited information about the road closures due to flooding, for example. But still, that is not enough for connected vehicles and or for the autonomous vehicles to understand exactly how the lanes are laid out. And our focus has been in this particular project mainly on the vehicle side of the requirements. And in particularly, since you heard about me from an automaker's perspective, from OEM's perspective, it is important to know the layout of a lane and how the lanes are configured and or laid out so that we can inform the driver, the applications running in the vehicle can inform the driver accordingly and when it is only necessary. Case in point is when you are driving on a work zone and let's say the lane is closed, the rightmost lane is closed. If the vehicle is going on the rightmost lane, then only it is necessary to inform the driver that you need to change the lane at such and such point and watch out for lane changes. But if it is already on the other lanes that are already open, there's no need to provide additional information or repeat the information, primarily because it just tries to avoid driver workload. So that is the reason why we're focusing on the high fidelity lane level mapping for these applications. Next, please. Okay, so what we need to do that? We need a proper and accurate infrastructure maps are crucial for this kind of applications. The ability to easily generate and validate, transmit accurate, high fidelity lane level digital maps are the key part of defining an infrastructure level map. in a wide-scale implementation using the consistent mapping methodology. When we were developing these applications during 2018 timeframe, and this is the whole project was done during that time, we realized that when you are trying to develop a map using a Google Earth type of satellite view to select a node points to define the map itself, it's very tedious, laborious, and error-prone process. And there has to be a better way than doing that. So this is the project in which we developed this mapping tool, which I'll talk about it. But the whole purpose there is the consistency in development of the map is very important. And how it is developed is very important so that the application running on the vehicle side exactly knows how the lanes are laid out. Next, please. So this chart shows the reasons for why a dynamic and algorithmic way of developing map is necessary. You look at on the top right diagram where there's a curvature. And if you define that curvature in an arbitrary way, the way the map requirements for the vehicle side works, that vehicle needs to understand which lane it is on. And while it is on a curvature, it is difficult for vehicle to realize if it's on the current lane or it's an adjoining lane. The way it is defined is that it's a virtual bounding box that defines where the position of the vehicle should be in order for it to know which lane it is on. Now, if you are trying to draw a bounding box using those three node points that you see that, what happens in that case that a large portion of this bounding box falls into the adjoining lane. And when the vehicle is on that adjoining lane, it thinks it is in a current lane or it thinks it's an adjoining lane. So it gives you a lot of false positives or false negative in that case. So the dynamic positioning of those nodes that defines how the lanes are laid out is very critical for this purpose. Next, please. So what we developed is called software toolchain to build work zone map and messages. And when I say message, it means the RSM that we heard a number of times. RSM is a road safety message, which was developed at camp during this project in 2017 and 18 timeframe. And it was pushed to SAE for one of those standardization. And that work is still continuing primarily because the standard is not out yet, but the basic, I shouldn't say basic, foundational work, as well as all the requirements have been defined, and so as the UPRA encoding for those messages also been defined. So this particular software toolchain consisting of several steps, as you can see. And what Tony discussed about it also is called collecting the information for the vehicle from vehicle path, meaning that a vehicle can be driven on an open lane in a work zone, and we collect the data about its path. And this data is collected at 10 hertz. So for a 15-mile long work zone, you have a large amount of data points coming from the vehicle position. Now, the map message definition defined in SAE cannot accommodate this large number of data in the message itself. So there needs to be a way to reduce this data to a point so that it can be represented as a map message or RSM message in this particular case. So the first step is to collect a high resolution data points using the good quality or high resolution quality differential GPS so that an accurate positioning of the data of the vehicle is collected. Once that is collected, then the software goes out and generates an algorithm that goes out and selects selective points that actually defines the map for this lane. Which then becomes a part of, which then is represented in RSM. But in between the collecting the data, creating the node points, and generating the RSM, there are a couple other steps it goes through. It also generates an XML version of the map message, which then converted into a binary format. This XML version provides user or the map generator to see the map is there and look at the value in a human readable format, and if they need to change any information there. It also generates required data so that it can be overlaid on a Google map so you can literally see and visualize the map itself. Second, after that point, once everything is visually verified as well as the data integrity is verified by the user, that you generate a step that actually converts those XML file into RSM, the road safety message. The road safety message is a binary encoded, encoded message that is now ready to transmit via a roadside unit so that that information is available, made available to the vehicles that are approaching the work zone. Next, please. Next, please. This one has a few animations, so please continue. Please continue. So what happens in that case once it is placed in a roadside unit, because it's already packaged to ready to transmit, then IEEE protocols are implemented along the line so that its security and secure messages are made available, and that can be transmitted or broadcast for the vehicle. Next slide, please. So what this is also, there are a bunch of animations here, shows you the different steps you go through, which I just described. Can you click one more time, please? So what you see it in animation, you are driving a vehicle through a work zone and actually collects the vehicle position data. That's all marked as a magenta color. While you are driving this vehicle, you can also mark where the lane closures or the tapers started, or the tapers are ended, where the workers are present, and so forth. Now, currently, when we developed this information about 3.5 years ago, we were still under the investigation of having an automated way to generate those things using things like icon or a arrow board that has GPS information included in that. However, the communication to collect that information was not ready yet at this point, so we could not utilize it. But this can be enhanced very easily by having those roadside sensors telling you where the lane closure starts and where the lane closure ends, where the workers are present, and that can be very easily integrated into the software so that dynamic changes can be accommodated and you don't need to redrive or drive through the work zone number of times to just get those updates. This particular software toolchain that we created consisting of 5 different pieces, as shown in the center there. Next, can you click one more time, please? So the software that generates the breadcrumb, as you will say, that collects the vehicle position information, once it knows that vehicle position information, it needs to know the configuration of the roadway that you laid out, which tells you how many lanes that is, which lane did you drive on, because you don't have to drive in a multiple times or multiple lanes to get that information. It is assuming and it is replicating that information by computing offsets from one lane to other lane. So the information is that configuration file looks at how the topology of that work zone is laid out and uses that information to construct the map. Next, please. So these are just different steps for constructing that. Go on, please. That step, which is you're seeing it on the right corner, is actually shows a graphical view on a Google Map to show you how the map is generated. The magenta dots that you see is actually the vehicle path points or the vehicle breadcrumb, and then on top of it, it overlays with icons where the node points are generated for the map, as well as where the workers are present, where the lanes are open or closed, and what are the speed changes. And each node point that you see can be also more detail is available. Once you put your mouse cursor on top of one of those node points, it will show you exactly what those node points and its characteristics are there. So this is exactly how the work zone application software is defined. Next, please. So this gives you an overview of what that visualization is talking about. On the left-hand side, it tells all the detail about the work zone itself. It tells you number of lanes there are, which lanes are closed, when was the data collected, so you know exactly when you did the mapping part of it, and in the bottom it talks about all this information about what are those icons mean, and their legends are defined. The arrow keys that shows things that can also actually animate, that can be animated, the way you drove the vehicle to collect the data, so you know exactly how the driving was done and what data you collected, so that can be animated, so it gives you all the visualization in that detail. The right-hand side of the screen, which shows you all the node points, also tells you where the lane closure started or ended, how many lanes are closed, what are the speed variations are happening in those locations, and so forth, is all defined. And visually, you can verify the mapping is as you intended, you meaning the agency intended before deploying the work zone application. Next, please. So what's our status? Like I mentioned, we developed this, and particularly is the vehicle-centric or vehicle-facing for the drivers. We developed this, and during the course of development, we used this software toolchain to map a large work zone in Texas DOT in collaboration with Texas Transportation Institute on the I-35 corridor in Texas. That was from north side of Austin going up to about 15 miles north. That was the piece of the work that was going on at that time. We also worked with the University of Arizona, and they used this mapping tool for their commercial vehicle information system and network, so CVISN, for freight vehicle work zone project. They are doing an elaborate project on that area, and they use this mapping tool to actually map and transmit those RSM messages for the freight vehicles in that area. We provided this, since, as I mentioned, this was funded by the contract through Federal Highway and Sexton Lab. We gave this software package and ran through many test cases there within the Sexton Lab itself at Federal Highway, which is at Turner Fairbanks. And they integrated this into a larger mapping tool. Virginia Tech has also incorporated this into their work zone software, which is for the Virginia Connected Corridor. And we made this available at a camp. The entire tool is open source that can be downloaded. And we have over 30 plus different agencies have downloaded, and they are using this tool at this point. Next, please. That concludes my presentation, and thank you for your time.
All right. Thank you very much, Jay, for your presentation. We can invite the panelists up to the stage again if they would like. We have just a couple of questions for them. Tony, I believe this first question is for you. It's not really clear because a lot of you had different information, but it came up early in the discussion. Sure. It's asking if your tool will be uploaded to Google Maps and other mapping software. You know, maybe not in the detail you're describing, but in some capacity.
Yeah, it sure can. So the API that we're using on the website to plot the WZDX as well as the RSM message is doing it on a Google map. That's how we've chosen to implement it, using the Google Map API. And then the files that you can download, the GeoJSON for the WZDX message, is real simple to plot on maps. That's sort of the cool thing about GeoJSON. There's lots of websites that you can just drop a GeoJSON file in and it'll plot it on a map for you, so you can host that in many different mapping software. So definitely.
All right, thank you. This next one, I think it's yours, Jayashri. It's from Paul Pisano. He said he just wants to confirm that the ODE is just software to support an actual data environment. it's not, as the name suggests, a bona fide operational environment that is actually sending and receiving data, correct? And I guess he just wants to confirm his understanding of what you were talking about.
Yeah, I'll actually have Tony answer that. He's worked
For sure.
on ODE a lot longer than me, so.
Yeah, the ODE environment is kind of an interesting thing. It's a set of Docker images. For the Wyoming Connected Vehicle Pilot, we run it internally in the TMC. For Colorado DOT, we run it in the Google Cloud Platform. At the Stoll, we run it in the AWS environment. So it's a very flexible tool that can run most anywhere. And it has a lot of different modules that can support privacy protection for BSMs. It can encode and decode traveler information messages or BSMs or SPAT messages, that kind of thing, and translate those between the ASN.1 and JSON. And then it has the ability to push those up to Kinesis Firehose or to Oracle or MongoDB or Google PubSub. So we have all of these different connectors for it that are supported. So it really is a pretty complete environment.
Great, thank you so much. This one's for you, Jay. It's asking, how is the worker presence data collected and who's it provided to, the DOT, the contractor, etc.?
So currently the workers present is something that DOT or agency provides where the workers are present. Like I said, if we have a mechanism through the workers wearing kind of vest, which is what Virginia Tech is doing, where the workers are wearing the vest and which has a way to communicate their position information to a receiver, and that receiver transmits that information to a backend where this data can be integrated into the larger map. So that's a thing that Virginia Tech is exploring. But currently in my software at this point is where we need to know where the workers are present so we can mark these areas. The reason for workers present is also because in many states it's required that when the workers are present, the speed drop takes place. And we need to inform and warn the driver accordingly that there's a change in speed. And when they are going above the speed, the warning system in the vehicle indicates that to the driver.
Perfect, thank you. And a kind of a follow-up question. It says, will the output support for, and this is again at you, Jay, will the output support primarily be traveler information applications, or is it high enough resolution, latency, et cetera, to support CAV operations?
It is more for the CAV applications. We started out with a connected vehicle, and keep that in mind. For a CAV, a high resolution map cannot be very quickly generated as the work zone dynamic configuration of work zone keeps on changing overnight. For example, you may have a lane closures in the nighttime and they open up in the daytime. Those kind of information cannot be really made available through the CAV for the CAV applications, just because you cannot go out and remap every time. So augmenting these node points, which says where the lane drops are taking place, those information can be augmented on top of the CAV map that gives them additional information for the CAV to know that there are lane closures coming up and they can do their driving accordingly.
Okay, good. And one final question here. I'm not quite sure who it's directed to, but it just asks if any of your case studies have used traveler information.
So let me just take that one. The traveler information. So when we worked with the Texas DOT, the SWRI, which is the Southwest Research Institute, was also part of this project. And they took the same information and converted into traveler information. So instead of telling the driver which lane they need to be, they are providing information where the lane closures are beginning, how far it is from your current position. So the vehicle driver knows that there is a upcoming lane closures or work zone coming up, and that provides them enough time to either take an alternate route or keep that in mind that they are going to be coming up to a work zone. So this kind of information is done through their project.
Thank you so much. Well, thank you to all of our panelists here that have shared information and provided very in-depth presentations. These presentations, again, will be available following. And I think any of you would be willing to take questions after the fact. And so if they're on, you can message them in the chat, or if not, we can follow up individually. So thank you so much for joining us today. We'll take our break now, and our next session coming up, and maybe Matt's going to announce this, will be at 2:15 on Smart Work Zone projects. So take it away, Matt.
Well, what he said. So we'll see you all here at 2:15. Thanks.